The National Electrical Code, or NEC, does not specify a minimum distance between a grounding grid and a building. However, it does require that the grounding electrode system be installed as close to the building as practicable, according to NEC section 250.46. A2. While the NEC does not require a specific distance, some recommendations are generally accepted as good practice. Firstly, minimize distance. The grounding grid should be installed as close to the building as practically possible to reduce the impedance of the grounding system. Secondly, avoid interference. The grounding grid should not be located where it could interfere with underground utilities or other important structures. Thirdly, maintain accessibility. The grounding grid should be located in an area where it can be easily inspected and maintained. In the case of a building with an excavation that exceeds the building perimeter, it is important to consider the following. Firstly, depth of excavation. The depth of the excavation should be sufficient to allow for proper installation of the grounding grid. Secondly, type of fill. The type of material used to fill the excavation, for example, stone, can affect the conductivity of the soil and the effectiveness of the grounding grid. Thirdly, access for testing. It is important to ensure that there is adequate access for future testing and maintenance of the grounding grid within the excavated area. Installing the grounding grid as close to the building as practicable within the excavated area is best practice. However, it is important to consider the depth of the excavation, the type of fill, and access for testing when determining the exact location of the grounding grid. Consulting with a qualified electrician or grounding expert to assess the specific site conditions and determine the most appropriate location for the grounding grid within the excavated area is recommended. The NEC guidelines prioritize safety and effectiveness in grounding systems, emphasizing proximity to the building while accommodating practical site conditions. Firstly, NEC section 250.46. A2 mandates the grounding electrode system to be as close as practicable. This directive aims to minimize impedance, ensuring a swift and efficient path for fault currents to ground, which is crucial for preventing electrical shock and equipment damage. Secondly, proximity helps in maintaining a low impedance path. Impedance, the total opposition to current flow in an alternating current circuit, includes resistance and reactance. A longer path increases impedance, reducing the effectiveness of the grounding system. By keeping the grounding grid close, the impedance is minimized, enhancing the system's ability to quickly clear faults. Thirdly, practical considerations often dictate the exact placement. While the NEC emphasizes proximity, it also acknowledges that site-specific conditions can influence the final location. These conditions might include the presence of underground utilities, the type of soil, and the physical layout of the building and its surroundings. Engineers and electricians must balance the NEC directive with these practical constraints. Avoiding interference with underground utilities is a critical aspect of grounding grid placement. Utility lines such as gas, water, and communication cables can be damaged by the installation or operation of a grounding system if not properly accounted for. Firstly, careful planning and surveying are necessary. Before any digging begins, it is essential to conduct a thorough survey of the site to identify the location of all underground utilities. This typically involves consulting with local utility companies and using specialized equipment to detect buried lines. Secondly, maintaining adequate clearance is important. The grounding grid should be positioned to ensure sufficient clearance from underground utilities, preventing any potential interference or damage. This clearance may vary depending on local regulations and the type of utility. Thirdly, proper installation techniques are crucial. When installing the grounding grid near underground utilities, it is important to use installation techniques that minimize the risk of damage. This might involve hand digging in sensitive areas or using non-conductive materials for certain components of the grounding system. Maintaining accessibility for inspection and maintenance is another key consideration. A grounding system is not a set-and-forget installation. It requires periodic inspection and maintenance to ensure its continued effectiveness. Firstly, ease of access is essential. The grounding grid should be located in an area where it can be easily accessed for inspection and maintenance. This might involve installing access points or manholes that allow technicians to reach the grid without having to excavate. Secondly, regular inspections are necessary. Regular inspections should be conducted to check for corrosion, damage, or loose connections in the grounding grid. These inspections can help identify potential problems before they lead to system failure. Thirdly, timely maintenance is crucial. Any issues identified during inspection should be addressed promptly to maintain the integrity of the grounding system. This might involve repairing damaged components, tightening connections, or replacing corroded sections of the grid. When dealing with excavations, several additional factors come into play. The depth of the excavation, the type of fill material, and the need for future testing all influence the optimal placement of the grounding grid. Firstly, the depth of the excavation must be sufficient. The excavation must be deep enough to allow for the proper installation of the grounding grid. This includes ensuring that the grid is buried below the frost line to prevent damage from freezing and thawing cycles. Secondly, the type of fill material affects conductivity. The material used to fill the excavation can significantly impact the conductivity of the soil and the effectiveness of the grounding grid. Materials with high conductivity, such as concrete, are preferred over those with low conductivity, such as gravel. Thirdly, access for future testing is essential. Adequate access must be provided for future testing and maintenance of the grounding grid within the excavated area. This might involve installing test wells or other access points that allow technicians to measure the resistance of the grounding system. Soil conditions play a vital role in the performance of a grounding system. Different types of soil have different levels of conductivity, which affects how well the grounding system can dissipate fault currents. Firstly, soil resistivity is a key factor. Soil resistivity is a measure of how well a particular type of soil conducts electricity. Soils with low resistivity, such as clay and loam, are better conductors than soils with high resistivity, such as sand and gravel. Secondly, soil moisture content matters. The moisture content of the soil can also affect its conductivity. Moist soil is a better conductor than dry soil. Therefore, it is important to consider the local climate and drainage conditions when designing a grounding system. Thirdly, soil treatment can improve conductivity. In areas with poor soil conditions, it may be necessary to treat the soil to improve its conductivity. This can be done by adding conductive materials, such as ground enhancement compounds, to the soil around the grounding grid. Ground enhancement materials, or GEMs, are specialized products designed to improve the conductivity of soil. They are often used in areas with poor soil conditions or where it is difficult to install a traditional grounding system. Firstly, GEMs can lower soil resistance. GEMs typically consist of a mixture of conductive materials such as copper sulfate, bentonite clay, and other additives. These materials help to lower the resistance of the soil, allowing fault currents to dissipate more easily. Secondly, GEMs can improve grounding effectiveness. By improving the conductivity of the soil, GEMs can enhance the effectiveness of the grounding system, reducing the risk of electrical shock and equipment damage. Thirdly, GEMs require proper application. GEMs must be applied correctly to be effective. This typically involves mixing the GEMs with water and pouring it into the soil around the grounding grid. It is important to follow the manufacturer's instructions carefully to ensure proper application. Proper grounding electrode selection is crucial for an effective grounding system. The NEC specifies several types of grounding electrodes that can be used, each with its own advantages and disadvantages. Firstly, ground rods are a common choice. Ground rods are metal rods that are driven into the ground to provide a path for fault currents to dissipate. They are relatively inexpensive and easy to install, making them a popular choice for many applications. Secondly, ground plates offer another option. Ground plates are metal plates that are buried in the ground to provide a grounding connection. They are typically used in areas where it is difficult to drive ground rods, such as rocky or sandy soil. Thirdly, concrete encased electrodes are also utilized. Concrete encased electrodes, also known as UFA-grounds, are grounding conductors that are encased in concrete. They are typically used in new construction projects and can provide a very effective grounding connection. The size and type of grounding conductor are also important considerations. The grounding conductor must be large enough to safely carry the maximum fault current that could occur on the system. Firstly, conductor size is determined by NEC tables. The NEC provides tables that specify the minimum size of grounding conductor required for different types of electrical systems. These tables take into account the size of the service entrance conductors and the type of grounding electrode used. Secondly, conductor material matters. Grounding conductors are typically made of copper or aluminum. Copper is a better conductor than aluminum, but it is also more expensive. Aluminum conductors must be larger than copper conductors to carry the same amount of current. Thirdly, conductor installation is critical. The grounding conductor must be installed properly to ensure a reliable grounding connection. This includes making sure that all connections are tight and corrosion resistant. Regular testing and maintenance are essential for ensuring the continued effectiveness of a grounding system. Grounding systems can degrade over time due to corrosion, damage, or loose connections. Firstly, regular inspections are necessary. Regular inspections should be conducted to check for any signs of damage or corrosion in the grounding system. This includes inspecting the grounding electrodes, grounding conductors, and all connections. Secondly, ground resistance testing is important. Ground resistance testing should be performed periodically to measure the resistance of the grounding system. This test can help identify potential problems before they lead to system failure. Thirdly, timely repairs are crucial. Any issues identified during inspections or testing should be addressed promptly to maintain the integrity of the grounding system. Consulting with a qualified electrician or grounding expert is highly recommended when designing and installing a grounding system. A professional can assess the specific site conditions and recommend the most appropriate grounding solution. Firstly, experts understand NEC requirements. A qualified electrician or grounding expert will be familiar with the NEC requirements for grounding systems and can ensure that the installation complies with all applicable codes. Secondly, they can assess site-specific conditions. A professional can assess the specific site conditions, such as soil type, moisture content, and the presence of underground utilities, to determine the most effective grounding solution. Thirdly, they can provide expert advice. A qualified electrician or grounding expert can provide expert advice on all aspects of grounding system design, installation, and maintenance. Addressing specific concerns about reluctance to install ground rods and test wells inside the excavated area is important. While the NEC doesn't explicitly prohibit this, several practical considerations come into play. Firstly, physical obstructions may exist. The presence of the stone fill, especially if it's densely packed, can make driving ground rods difficult or impossible without specialized equipment. Secondly, concerns about disturbing the fill are valid. Installing ground rods and test wells could potentially compromise the integrity of the fill, especially if it's designed to provide structural support or drainage. Thirdly, alternative grounding methods may be suitable. Depending on the specific site conditions and the requirements of the electrical system, alternative grounding methods such as ground plates or concrete-encased electrodes might be more appropriate. In summary, while the NEC emphasizes proximity to the building, the exact placement of the grounding grid should be determined based on a careful assessment of site-specific conditions, including the depth of the excavation, the type of fill material, the presence of underground utilities, and the need for future testing and maintenance. Consulting with a qualified electrician or grounding expert is essential to ensure that the grounding system is installed safely and effectively. Consider the building's purpose when evaluating the grounding system. Firstly, residential buildings necessitate effective grounding. Grounding systems in residential buildings safeguard against electrical shocks and protect sensitive electronics from voltage surges. Secondly, commercial buildings demand robust grounding. Commercial buildings often have more complex electrical systems and equipment, necessitating more robust grounding systems to handle higher fault currents and ensure safety. Thirdly, industrial facilities require specialized grounding. Industrial facilities with heavy machinery and specialized equipment may require specialized grounding systems to protect against equipment failure and ensure worker safety. Evaluate potential future expansions. Firstly, plan for increased load. Account for potential increases in electrical load due to future expansions or upgrades. Secondly, ensure grounding system scalability. Design the grounding system to be easily scalable to accommodate future needs without requiring major modifications. Thirdly, consider access points. Plan for future access points for testing and maintenance to facilitate future upgrades or repairs. Consider the impact of nearby metallic structures. Firstly, bonding to metallic structures is vital. Bond the grounding system to nearby metallic structures, such as fences, pipelines, or other utilities to minimize voltage differences and prevent stray currents. Secondly, corrosion concerns should be addressed. Take measures to prevent corrosion at the interface between the grounding system and metallic structures, such as using compatible materials and applying protective coatings. Thirdly, professional evaluation is recommended. Consult with a grounding expert to evaluate the potential impact of nearby metallic structures and ensure proper bonding and corrosion protection. Consider the local climate and environmental conditions. Firstly, corrosion in coastal areas is a concern. Coastal areas with high salt content in the air require grounding systems that are resistant to corrosion. Secondly, freezing and thawing cycles can affect grounding. Areas with freezing and thawing cycles can damage grounding electrodes and conductors, requiring the use of frost-resistant materials and installation techniques. Thirdly, areas with lightning strikes demand specialized grounding. Areas prone to frequent lightning strikes require specialized grounding systems to protect against lightning surges and prevent damage to electrical equipment. The grounding system's design should integrate with surge protection devices. Firstly, surge protection device coordination is essential. Coordinate the grounding system with surge protection devices, or SPDs, to provide a comprehensive protection against voltage surges caused by lightning or other transient events. Secondly, SPD placement is critical. Position SPD at strategic locations throughout the electrical system to divert surge currents to ground and protect sensitive equipment. Thirdly, grounding impedance is important for SPD. Ensure that the grounding system has low impedance to provide an effective path for surge currents to dissipate. Consider the grounding system as part of a comprehensive electrical safety plan. Firstly, regular training is necessary. Provide regular training to electrical personnel on the importance of grounding and the proper procedures for inspecting and maintaining grounding systems. Secondly, safety audits are essential. Conduct regular safety audits to identify potential hazards and ensure that the grounding system is functioning properly. Thirdly, emergency response plan should incorporate grounding. Incorporate grounding considerations into emergency response plans to ensure that electrical equipment can be safely de-energized in the event of a fire or other emergency. Consider the life cycle cost of the grounding system. Firstly, material selection impacts long-term cost. Evaluate the long-term cost of different grounding materials, taking into account factors such as corrosion resistance, maintenance requirements, and replacement frequency. Secondly, installation costs should be considered. Consider the initial installation costs of different grounding methods, including the cost of materials, labor, and equipment. Thirdly, maintenance costs must be factored in. Factor in the ongoing maintenance costs of the grounding system, including the cost of inspections, testing, and repairs. Consider the impact of the grounding system on the overall building design. Firstly, early planning is essential. Integrate grounding considerations into the early stages of building design to ensure that the grounding system is properly coordinated with other building systems. Secondly, aesthetics should be considered. Consider the aesthetic impact of the grounding system and choose materials and installation methods that minimize its visibility. Thirdly, space allocation matters. Allocate sufficient space for grounding equipment and conductors to ensure that they can be installed and maintained safely and effectively. Consider the specific requirements of sensitive electronic equipment. Firstly, dedicated grounding is sometimes needed. Sensitive electronic equipment, such as computer servers and medical devices, may require dedicated grounding systems to minimize electrical noise and prevent equipment malfunction. Secondly, isolated grounding can be beneficial. Isolated grounding systems can provide a cleaner ground reference for sensitive equipment by isolating the equipment ground from the building ground. Thirdly, shielded cables are sometimes necessary. Shielded cables can help reduce electrical noise and interference by providing a conductive barrier around the signal conductors. Consult with equipment manufacturers and grounding experts to determine the specific grounding requirements for sensitive electronic equipment. Consider the implications of changes to the electrical system. Firstly, re-evaluation after upgrades is necessary. Re-evaluate the grounding system whenever changes are made to the electrical system, such as adding new equipment or upgrading existing equipment. Secondly, potential for increased fault current must be considered. Ensure that the grounding system is capable of handling the increased fault current that may result from changes to the electrical system. Thirdly, updated documentation is vital. Update the grounding system documentation to reflect any changes that have been made.